All right, it's 1:20 Pacific, and hello everyone. Back to application session in today's CHIUW. We have our last talk in this session by Nikhil Padmanabhan from Yale. He'll be talking about simulating ultralight dark matter with Chapel.
Thanks, Enkin. So I'm assuming you can hear me just fine. Thanks for the opportunity to come out and talk about some of the research that's been going on within our group that's been aided in large part by having access to Chapel. This is work largely led by my graduate student, Luna Zagorak, and you'll see Elliot's fingerprints over a large amount of the optimization work out there. So what I'm going to talk about today is our efforts to simulate ultralight dark matter in Chapel and what we've learned from it up till now. So since I'm talking about dark matter in an astrophysical context, I thought I'd start off by giving you a little cartoon that you can sort of keep in your mind as you sort of run through this talk about when we talk about dark matter, what we really mean. And that's what we really are talking about is the fact that if you look at the universe and you look at where we have luminous matter in the universe, stuff that we're all made out of, and ask where is all of the matter, most of that matter isn't in the luminous matter, but it's in these dark matter halos that surround this luminous matter. And so here's the cartoon that you should go around with, which is, here's a picture of a galaxy that you're used to thinking about as the constituents of the universe, and really every galaxy comes with its own dark matter halo. And we can see this dark matter halo in a number of different probes that go through here. So a couple of things to sort of just tell you a little bit about what dark matter is. If you ask a cosmologist, which I am, how much of the universe is made out of dark matter, they'll tell you about 80% of the matter in the universe is dark. And when we say dark, we really mean particles that you and we've never seen either in a lab or in a direct experiment on Earth out here. So it's only been inferred astrophysically. These dark matter particles form gravitationally bound structures. You just saw an example of one on the previous slide, these dark matter halos out here. And there's been a traditional model of a dark matter particle, which has gone by the name of a WIMP, which is a weakly interacting massive particle. And these have been heavy particles. And by heavy, I mean something which is about 100 times the mass of a proton. Now, the reason we're all so enamored with this idea of dark matter is it's had a large number of successes. It explains a large scale of observations from rotations of galaxies to clusters of galaxies sort of shooting through one another and how they interact, to sort of the largest scales that we can observe in the universe, mapping out what the distribution of galaxies is, all the way out to sort of the earliest light that we see from the Big Bang out here. And having this 80% of the universe be this non-baryonic, which is basically not stuff that you and I are made out of, dark matter, explains a whole host of these observations out here. There are, however, challenges to this model. There are a number of puzzles that remain on small scales. This regular weakly interacting massive particle, if you run numerical simulations of it, seems to cluster more strongly than the dark matter, than the observations seem to suggest. We don't see as many small dark matter halos around in places. And so there are interesting challenges. And so that sort of has motivated people to think about alternative models for dark matter. Another piece that's motivated this is the fact that we've never really detected these in the lab or on accelerators, and so we'd like to go out and find these pieces. So people have come up with dark matter candidates. There's a whole host of them. They run from the entire mass range, and there's a large number when you get an XKCD comic about it. And the dark matter that I'm going to be talking about is way off to the left of this graph out here. So this is pieces that are certain micro electron volts in weight, and really we're talking about things that are about 10 to minus 22 electron volts. Now, one of the nice things about this is that when you get to such light particles, the quantum mechanics of these particles becomes astrophysically interesting, and so you expect a whole host of different physical properties and phenomenology than you would normally see with regular dark matter. You see, for instance, the wave properties of this dark matter in a lot more detail. So you can see things like interference patterns. It has a high enough density that it can form Bose-Einstein condensates. And probably for this talk here, the most important piece here is to calculate anything about this dark matter beyond sort of the most trivial and idealized situations requires actually doing a simulation. And so we were led to thinking about simulating this dark matter. And this is a relatively new model. And so we've been spending a lot of time trying to do numerical experiments, trying to understand how well we can understand the behavior of this dark matter. And so we wanted a code that we could do a number of numerical experiments with. A key requirement was scalability. And this was it. We needed to be able to resolve the cause of these halos. So we needed a relatively large dynamic range. And then the simulation time scaled is roughly n to the fifth, where n is sort of your grid side that you were simulating these particles on, these systems on. And so if you need to scale this out to a relatively large number, a high resolution grid, you needed to be able to scale this to a relatively large system out here. Our initial approach to this project started off actually not with Chapel, but with Python. A collaborator of mine, Richard Easter, had an initial code in Python driven by a Jupyter notebook. And one of the great advantages of this was it was very easy to use and modify, allowing us to do a number of numerical experiments with the code. It was relatively performant for a Python code, multi-threaded. It made use of all of the tricks that we've learned to do pieces. But as we started extending it, we started to hit more and more Python bottlenecks. And so we attempted to port this over to Chapel, both starting off with a single locale version and then out to a multi-locale version. And what we'll show you today are the results from this. So let me start talking about the system we're solving and the actual code. So we're solving these two equations. We're just evolving these equations forward in time. The first equation up top is the Schrödinger equation, and the second one is the regular Poisson equation to work out what the gravitational potential is. And the key piece to notice about both of these equations is that critical elements in calculating both the Schrödinger equation and the gravitational potential require running FFTs. The algorithms are most easily expressed if I can go back and forth into Fourier space and back. And so if we wanted to run a distributed code, having a good distributed FFT was a key component of this code. Now, when you turn to distributed FFTs, the first question you have to ask is, how do you want to distribute your data? The simplest way to do it is what's a one-dimensional or a slab decomposition, where you just distribute one of the dimensions, this is a three-dimensional grid, only one of the dimensions along all of your locales, and you keep the others local to each node out here. This has an obvious problem, which is it doesn't scale very well, especially if you're in an MPI-like world. And so a lot of people went out to thinking about these two-dimensional decompositions, or these so-called pencil decompositions. And these you can now, because you've sort of distributed in two directions, you have a lot more scalability. One of the things we realized early on, though, was this limit to scalability here hurts the most with MPI codes. But with Chapel being this mixture of both MPI, both distributed plus local parallel pieces, we could get away with just doing a one-dimensional decomposition. And I'll show you that that actually doesn't limit us at all in our calculations out here. So what does a distributed FFT look like? Well, you distribute the array, and then you basically do three Fourier transforms. You Fourier transform in the two dimensions that are local to you, and then you transpose two of your dimensions, and then do your last Fourier transform out here. So writing down the pencil and paper version of this code was relatively simple. And so we said, let's ask what it would take to do this in Chapel. We use FFTW to do all of the one-dimensional local serial transforms. So we're not trying to beat tuned one-dimensional serial codes. We're really here thinking about the data movement that FFTs bring with them. So here's a naive implementation of this code. You basically do a loop over all of your locales, doing your Y, Z, and then I've alighted the X transform out here. And I've highlighted some of the various little pieces of the Chapel that are nice. The piece that was the nicest for me was that the transpose operation in a PGAS language was literally this one-line assignment statement that you could get away with out here. And I'll show you some of the performance that this naive code would do. But the point I'd like you to take away from this is this very closely follows the pencil and paper version of the world. So for someone not focusing on the performance and just translating algorithms, the algorithms translate very nicely in Chapel. There is one little piece that we had to immediately do, even with this naive version, to sort of reduce some of the congestion, which is we don't sort of, when we do these loops and we start doing this transpose, we make sure that we don't hit all of the same node synchronously all the time. And so we wrote a little offset iterator to sort of scatter things, and so that you would reduce some of the congestion in communications. And so here's how well you do. This is this initial line out here. And to tease the result that's coming up, here's the final performance that we got out with the code. And so let me show you what one has to do to go from the naive version to this fuller version out here. Focusing on one piece of the code, there are three things we ended up doing. We ended up overlapping computation and communication, which we were able to do even though the communication out here was not non-blocking, but blocking communication. But each of the individual tasks on every node could start off a communication job, and so that kept the nodes relatively busy. We had to sort of break away from that very simple PGAS model that I showed you before and actually do some low-level communication to avoid overheads from slicing of arrays. And then an optimization we did here that I'm not showing you is batching the FFTW call, so we didn't have to keep going back and forth to the C version out here. So let me show you some benchmarks. I'll skip these. You can see these in the slides. Here are the benchmarks. These are for the NAS NPB Fourier transform version, and there are 3 separate classes. Each class is 8 times bigger than the other, and we're comparing a reference MPI and UPC code with Chapel, and now this is the fully optimized version. And you can see Chapel beats both the MPI and is on par with the UPC code once you get to larger scale problems, all the way out to very large numbers of locale counts out here. So we were very happy with these results. It basically meant that without a whole lot of work, we were able to take an FFT algorithm and get good scaling performance across the entire system. So let me show you the timings results for the full system itself. Out here, these are the timings for the entire simulation, not just the FFT, running for different grid sizes from 512 all the way out to 4096. And you can see both that you get good, strong scaling as you increase the number of locales, and also relatively good weak scaling as we increase the problem size, matching it to. In fact, if you take these 2 points, they basically are a factor of 8 apart, both in the number of locales and the problem size that we're considering out here. So great. So that's one piece of writing a research code. There's another set of pieces that you have to deal with when you write up a research code. There's a bunch of plumbing that you have to deal with, and we benefited from a lot of the work that was done, I think, for Arcuda with parallel HDF5. We wrote a version of wrapping HDF5 tables so we could directly serialize arrays of records. And all of these are good examples of just benefiting from very good C interoperability, because we were able to sort of use tools that could then be used later down the line for analysis methods. When you think about the other piece of a research code, you want to be thinking about analysis steps, and those analysis steps quite often involve running things in line with your code, so they need to be relatively fast. One of the standard things we ended up doing are calculating profiles and histograms out here, and these get modified pretty often, so you don't want to be introducing bottlenecks into the code. And so let me just show you one of those bottlenecks that we recently tripped over with this out here, which is computing a density profile or a histogram in these pieces. If you look through this is the way you would simply compute one with an overall reduction. This is an incredibly elegant code. If you look at the timings for this code, on the other hand, though, as you start increasing the number of locales, you start seeing it get slower and slower out here. And so you can say, where is this coming from? This appears to be from the reduction getting slower. So we looked at various ways we could sort of make this a little bit more complicated, getting more and more Baroque out here. I'm comparing this with an atomic version of the world. The atomic contention hurt us in the early low locale counts out here. We had versions of the code where we were looking at an SPMD-like local reduction, and that worked pretty well for what we were doing. And you see good performance out here. But one of the key pieces here was that we were doing a local manual reduction. And so for fun, I asked, what would you get if you had sort of run the MPI version of this code, of the local reduction, by just calling it to MPI reduce? And you can see you get very good performance out there. And I don't want to sort of leave you with a feeling here that this was the only thing you needed to do. It really does depend on which parts of the code were slow, but it gives you a sense of the kinds of bottlenecks we've hit and the ways in which we've thought about solving them out there. So let me close out by just giving you a little bit of a flavor for what the science we've been doing with this. I'm going to just show you some movies of these codes, of what happens when we run this code. We're going to take two of these blobs of this ultralight dark matter and collide them with one another. And the kinds of questions we're asking are, what does the final state of the system look like? What are the various timescales that are involved in this system out there? So let me switch and just swing over to show you some of these movies. And so you'll see here two of these blobs. This is all powered by Chapel, except the plotting, but all of the analysis is happening. This is the mass colliding and forming this central soliton. This is showing you where the momentum in the system is, and you can see this object seems to be rotating out here, and we plot what the cumulative mass of the soliton and the cumulative energy looks like out here. This was for a case of equal mass collisions, and I can actually zoom in to a close-in version of this. And so this shows you the same thing in a little bit more detail. And you can start to see some of the momentum pictures that are happening out here, and you can see in a lot more detail with what's going on with the mass. But we are also interested in cases where we look at unequal mass collisions. And so let me just jump to the unequal mass version of the world. And here these are two very different mass blobs that got thrown together. And again, you're watching what's going on. And one of the questions we're asking is, for instance, is this a stable system? Does this lose energy with time? And so you can see for the cases that we're running out here, this looks like a remarkably stable system. So let me come back to where we ended up. These were just snapshots from this. People have already identified this. These were some of the things we learned while we were thinking about Chapel, where we could have benefited from a little better tooling, some ways and cases to express low-level communication or to not require it if we could get away with it, and these hidden performance traps that lay through. I should add that none of these are new issues to the Chapel team. Many are sort of issues that are tracked on GitHub. So I'll end here with my final thoughts. This is, I'm using this play on HPC, where P could be both productivity and performance. And I think Chapel now checks both boxes. It's a remarkably productive language to work in, but it's incredibly performant as well. I've been writing Chapel now for a few years. It's an incredibly fun language to write. It's very easy to throw prototype code in and largely does the right thing. And I'm getting to the point where I'm just working in Chapel these days. So let me stop here and take any questions.
Thanks a lot, Nikhil. As usual, really great talk. We have one question in the Q&A box. How do the problem sizes you're running today compare to those that you ultimately want and need to make good progress with the ULDM study and challenge?
Yeah, that's a great question. We need a couple of different kinds of problem cases we need to run. Because in some of these cases we're doing large parameter sweeps, so we need to run not just a single large box, but we want to run a very large number of smaller boxes. And we're pretty regularly running 512 and 1024 cubed cases there. And the win that we're finding out there with Chapel is not the fact that you couldn't do the box, it's that we can do the box very efficiently. And so we can just go through a large range of parameter space. We're gearing up to thinking about some very much larger runs. And I suspect we can get those runs running through. The largest case we've run is a 4096 cube run, which is pretty much where we think what we need in terms of resolution.
All right, thanks. The next question, Brian Dolan says, I think Chapel has an FFT library, but you did not use it. Can you share why? And where else did you have to appeal to external C libraries?
So I don't think Chapel has a native FFT library. I believe it has it has a wrapper to FFTW. We chose not to do a direct, so we chose to stick to the serial FFTs just because those have been significantly optimized, and we didn't want to go down the route of re-optimizing all of those, rewriting all of those and trying to relearn many years worth of research there. We chose not to do an MPI route out here, in large part because there were sort of impedance mismatches between trying to get the MPI code talking to the Chapel code, where the MPI code ideally would want to run, the MPI FFTW library wants to run without a hybrid MPI OpenMP mode. That's where it's the most efficient. And so that doesn't quite scale nicely with what Chapel does out there. The other places for external C libraries were mostly places where we wanted file formats and things like that. So we wanted to read in things easily and dump them out into formats that other people had readers to deal with. Brad's question here is this generating results that would be publishable in key astrophysics venues? And I think the answer is yes. So Luna's been working on getting an initial paper written with some of these binary collisions, and that's not a performance paper at all. It's purely an astrophysics paper. And so this is at the point now where this is a code. We're not actually fiddling with the code at all in terms of performance. We're really just adding in new science modules at this point.
I had actually a similar question to this in the sense of the code that you're developing. Obviously, I'm totally unfamiliar with your field, and I was wondering, like, the code that you develop, can it be developed into some product for other astrophysicists, or is it too specific to your personal studies?
I think it'll be useful for people doing very similar kinds of things. I think a lot of the tools, though, like the FFTs and stuff like that, get used across a whole range of astrophysics and a whole range of everything. So we hope those pieces, I think, will be more generally useful. The exact ultralight dark matter code, I think, will be useful for the people who care about ultralight dark matter.
Okay, thanks. We still have 2 minutes before we have to let Nikhil go, I guess, until 1:45. If anybody has any questions, that was a good time to ask.
I just wanted to comment on how gracefully Nikhil handled that question about FFTW. Specifically, Nikhil is the one who originally contributed back the Chapel module that wraps FFTW, so he's quite familiar with it.
Sorry, I'm not quite sure I understand Brian's in terms of the exact property. So we were looking, so I'll do my best. We're looking at the gravitational interactions between these, but they're interesting in that they're gravitational interactions of things that behave a lot more like fluids than they would just point particles. And so there's a lot more structure in that gravitational interaction that happens. Hopefully that answered your question. I'm happy to sort of, yeah, it's a small size. So Brian asked, was the differences, the fluid piece comes from the fact that these are very light particles. And so the quantum mechanics, basically the wave-like structure of those particles becomes more apparent.
Okay. I think that would be all, and it's 1:45 Pacific. Thanks again, Nikhil, for the great talk and great work. It was amazing and fun to listen. All right, thanks everybody. This also concludes the applications of Chapel session of CHIUW. In 10 minutes, at 1:55 Pacific, we will start Chapel on GPU session. Thanks for attending.